So now that we have been able to express our d sigma, I think we're pretty close to evaluating the integral itself. And one thing I do want to point out that might have been nagging you from the end of the last video. At the end of the last video, I took the principal root of the cosine of the principal root of cosine squared of t, and I simplified that to just being cosine of t. And you might have said, wait, what if cosine of t evaluated to a negative number? If I then squared it would be positive, and then if I took the principal root of that, I would then get the positive version of it. I would essentially get the absolute value of the cosine of t. And the reason why we were able to do this in particular in this video, or in this problem, is because we saw t takes on values between negative pi over 2 and positive pi over 2. And so cosine of anything that's either in the first or the fourth quadrant, so this is t right over here, the cosine will always be positive for our purposes, for the sake of this surface integral. Cosine of t is always going to be positive, and so in this case, we don't have to write absolute value of cosine of t, we can just write cosine of t. And so hopefully that makes you satisfied. That was just based on how we parameterized the t. Now with that out of the way, let's actually evaluate the integral. Our original integral, just to remind us, was the surface integral of x squared d sigma. We already know what d sigma is. Now we just have to write x squared in terms of the parameters. Well, we know the parameterization of x. The x in terms of the parameters right over here is cosine. This is our parameterization. X is going to be equal to cosine t cosine of s. Let me write that down. X of s and t is equal to, I already forgot, I have a horrible memory, is equal to, we have to go back to the original parameterization, not these partial derivatives, cosine t cosine s. Cosine t cosine s. Cosine t and then cosine s. And we're taking the integral of that squared. So let's think about this a little bit. So let's just this part right over here. If we square x, we're going to get cosine squared t cosine squared s. Cosine squared s. That's the x squared part right over there. And then you have the d sigma, which is this stuff, which is times cosine, I'm doing that same green, I want to confuse you with different shades of colors, times cosine of t ds dt. And now that we have this in terms of the parameters, the differential of the parameters, this essentially becomes a double integral with respect to these two parameters. And the good thing is that the boundary is pretty straightforward with respect to s and t. S takes on all values. S takes on all values between 0 and 2 pi. T takes on all values between negative 2 pi and, negative pi over 2 and positive pi over 2. So first, the way I wrote over here, we're going to integrate with respect to s first. S goes between 0 and 2 pi, and then t, let me clear, this is s, and then t will go between negative pi over 2 and positive pi over 2. And so let's see if we can simplify this a little bit. This is equal to the double integral over that same region, over that same area, I guess we could call it, over that same area of, well, now we have this cosine squared of t, and then we have another cosine of t right over there. So let me just write it this way. It's cosine to the third of t times cosine squared of s, and then ds, I'm going to color code it a little bit, ds, and so this is the integral for the ds part, and then dt, and then dt. And this is when we integrate with respect to s, notice these two, the t parts and the s part, they're just multiplied by each other. So when we're taking the integral with respect to s, this cosine cubed of t really is just a constant. We can factor it out. And it could look something like this. So let me rewrite it. This could be the integral from t goes from, I'll rewrite the boundaries, negative pi over 2 to positive pi over 2, cosine cubed of t, I just factor that out, and then I'll write the s part, times the integral, s is going to go between 0 and 2 pi, and I'll write this in blue, cosine squared of s, ds, and then you have dt out there. You have dt, let me do the dt in green, dt in green. That same green. dt. And now this outer sum, we can view it, you essentially view it as the product, well, of all of this business right over here. This thing has no t's involved in it whatsoever, so we can rewrite this. We can rewrite this, and I'll write all the stuff involving the t's as green. So we can rewrite this as pi over 2 from negative pi over 2 to pi over 2 cosine cubed of t dt times the integral. And I'm really just rearranging things. I guess you could kind of view this as the associative property, or I guess the commutative property. Those things always confuse me. Times the integral of 0 to 2 pi of cosine squared of s ds. And you didn't have to do it this way. You could have just evaluated it while it was kind of mixed like this. But this will help us kind of work through the trigonometry a little bit easier. Now, to solve these two integrals, we just have to resort to our trigonometry. Cosine squared of s, we can rewrite that as 1/2 plus 1. Actually, let me do that same blue color so we don't get confused. That is the same thing as 1/2 plus 1/2 cosine of 2s. And cosine cubed t, well, that's the same thing. Let's see, we can factor out a cosine of t. So let me rewrite. Let's just do it. Well, let me just do it both at the same time. Just get all the trigonometry out of the way. This right over here can be rewritten as cosine of t times cosine squared of t. Cosine squared of t. And the intuition here is if we can get a product of a sine doing something with a cosine, because cosine is sine's derivative, that's kind of, u substitution. You see a function and its derivative, you can just kind of treat it as a variable. So that's what we're trying to get to right over here. So cosine squared of t can be rewritten as 1 minus sine squared of t. So this is cosine of t times 1 minus sine squared of t. And so we can rewrite this as cosine of t minus cosine of t sine squared of t. And you might say, wait, this looked a lot simpler than this down here. That is true. It looks simpler, but it's easier to take the antiderivative of this. Easier to take the antiderivative of cosine of t. And even over here, you have derivative of sine of t, which is cosine of t. And so essentially you can do u substitution, which you probably can do in your head now. So let's evaluate each of these integrals. So this one, let me rewrite them just so we don't get too confused. So we have the integral from negative pi over 2 to pi over 2 of cosine of t minus cosine of t sine squared of t dt times the integral from 0 to 2 pi of 1/2 plus 1/2 cosine of 2s ds. Now we are ready to take some antiderivatives. The antiderivative of this right over here is going to be the antiderivative of cosine t. Well, that's just sine t. And then right over here, the derivative of sine t is cosine of t. So we can just essentially, if you wanted to do u substitution, you would say u is equal to sine of t, du is equal to cosine of t dt, and you do all of that. But what you probably can now do in your head is, okay, I have the sine t's derivative there, so I can treat sine t just like I would treat a t, or I would treat an x. So this is going to be, you still have this negative sign, minus sine to the third of t over 3. If this was just a t squared, the antiderivative would be t to the third over 3. But now, since we have its derivative, we can kind of treat it the same way, which is essentially doing u substitution in our head. So that's that. And we're going to evaluate it from negative pi over 2 to pi over 2. And so this is equal to, if you evaluated it at pi over 2, sine of pi over 2 is 1. So it's 1 minus 1 over 3. So that's just 2/3. Actually, let me not write it that way. I don't want to confuse people. And then minus sine of negative pi over 2. Well, that's going to be negative 1. Minus sine of negative pi over 2 is negative 1 to the third power is negative 1. So this is negative 1/3. Minus negative 1/3. And so this is going to be equal to, this is 2/3. And then this is negative 1 plus 1/3, which is negative 2/3. But then you have a negative out front, so this is plus 2/3 again. So this part at least evaluates to 4/3. This part, all this is really the home stretch. That all evaluates to 4/3. Now this part right over here, antiderivative of 1/2 is just 1/2 t. It's just 1/2 t. Antiderivative of cosine of 2s. Well, ideally you would have a 2 out front here. Out front, let me make this clear. So if I were to take the antiderivative of cosine of 2s, ideally you would want a 2 out here, so you have the derivative of the 2s. So you could put a 2 out front, but then you would have to put a 1/2 out front so that you're not changing the value of it. And of course you would have a ds right over here. I'm just taking a general antiderivative. But once you have it like this, then this is just like taking the antiderivative of cosine of s. This becomes, antiderivative of cosine is sine. So this will become sine of s. So this right over here is just sine of s. And then you have the 1/2 out front times 1/2. But then, of course, and you would have a plus a constant if you were taking an indefinite integral, but we're taking a definite one, so you don't have to worry about the constant. So just the antiderivative of cosine of 2s, just the antiderivative of cosine of 2s is 1/2 sine of s. And so you have this constant out front. 1/2 times 1/2 is 1/4. So it's going to be plus 1/4 sine of 2s. Sine of 2s. That's the antiderivative. And now we're going to evaluate it from 0 to 2 pi. And in either situation, this thing's going to evaluate to 0. Sine of 0 is 0. Sine of 4 pi is 0. And so you're going to have 1/2 times 2 pi, which is just pi, plus 0, because sine of 4 pi is 0, minus 1/2 times 0 is 0, 1/4 times sine of 0 is 0. So you're essentially just going to end up with pi. So this whole thing right over here evaluates to pi. And so we're done. You take the product of these two things, 4/3 times pi. Our entire surface integral evaluates to 4/3 pi. So this is equal to 4/3 pi, which is neat. If you have a sphere of radius 1, its surface area, or actually no, I shouldn't even go that because let me be very careful. I shouldn't make that statement because this wasn't just with respect to 1. But we have at least evaluated the surface integral, and we deserve I think a bit of a rest now.